Today I talk about spectral theorem. Also discuss now. It is important for functional analysis. Spectral theorem for compact self-adjoint operator. We also discuss self-adjoint operator and compact operator. We also discussed in previous class. Now spectral theorem for compact and self-adjoint operator. We now discuss this topic. First, let T V to V be a normal matrix. Be a normal matrix on a finite dimensional complex vector space V. Complex vector space V. Suppose that lambda 1, lambda 2, lambda n are distinct eigenvalues of T and mi I equal to 1 2 n with the corresponding eigenspaces. With the corresponding eigenspaces and P V to V the orthogonal projectional operator with the orthogonal projection onto mi. Then by finite dimensional spectral theorem, finite dimensional spectral theorem, we have I equal to summation pk k equal to 1 to n pk and t equal to k equal to 1 to n lambda k pk. Okay, then next we discuss some definition. Here we write just let T V to V be a normal matrix on a finite dimensional complex vector space V. Suppose these are distinct eigenvalues of T and mi be the corresponding eigenspaces and P V to V be the orthogonal projection onto mi. Then by finite dimensional spectral theorem we have this one. I equal to summation k equal to 1 to n pk and t equal to summation k equal to 1 to n lambda k pk. Okay, then we write this definition. Let T h1 to h2 be linear. Then T is said to be then T is said to be bounded if and only if TB is bounded in H2 for every bounded subset B of H1. Bounded subset for every bounded subset B of H1. Here is our portion. For every bounded subset B of H1. If H1 and H2 are Hilbert spaces, if H1 and H2 are Hilbert spaces, Hilbert spaces, and T H1 to H2 be a bounded operator, be a bounded operator, then T belongs to B H1 H2 if H1 equal to H2 equal to H, then B of H1 H2 equal to BH. The unit sphere of Hilbert space H is denoted by this one. Then next we talk about here the unit sphere, the unit sphere of Hilbert space H, Hilbert space H is denoted by SH. Okay, now we erase this portion. Here we talk about T one operator bounded when, and this one is some unit sphere of Hilbert space H is denoted by SH. Okay, not here given, and obviously T belongs to H1 to H2, and obviously T bounded. Then T belongs to B of H1 H2, and H1 H2 equal to same. Then obviously we write it BH. Okay, now we're going to further discussion about something. We erase this portion. We write just theorem. let T H1 to H2 be linear, then the following are equivalent. Then the following are equivalent. First one, T be bounded. Second one, T is continuous at 0. T is continuous at 0. Third one, T be uniformly continuous. T be uniformly continuous. Fourth one, there exists m greater than 0 such that norm of Tx less than equal to m norm of x for all x belongs to H1. Okay, then we also talk about some definition. Okay, write this definition here. If T be bounded, if T be bounded, then supremum of Tx less than infinity. Then supremum of norm of Tx less than plus infinity. And this quantity is called the norm of T and is denoted by norm T. Obviously, this quantity is called the norm of T, and is denoted by norm T, is denoted by norm T. Okay, so we just write this one, definition of norm T, and how we handle if T linear, then bounded, then continuous, then uniformly continuous, then obviously again bounded. Just we write this one. Again we write another theorem. In theorem pattern we write it. Here theorem, let T belongs to B of H1, H2, then the following are equivalent. Then the following are equivalent. First one, norm of T equal to supremum of norm of Tx such that x belongs to this is H1. That means this one is the some sphere of Hilbert space H1. Okay, then next we talk about here, right, 2 norm T equal to supremum of norm of Tx such that x belongs to h1 and norm of x less than equal to 1. Okay, and again norm of tx we define in another way. This one can be possible. We erase a portion, then going to forward or further discussion of norm t. Norm t equal to supremum of norm of tx divided by norm of x such that x belongs to h1. Number 4, norm of t equal to infimum of k greater than 0 such that norm of tx less than equal to k norm of x for all x belongs to h1. Okay, then then this 4 way will also represent norm. Okay, again we also write here norm t is the radius of the smallest ball, is the radius of the smallest ball containing the image of the unit ball in h1, containing the image of the unit ball in h1. So we also discuss about norm t. Okay, now we erase all portions and going to another definition of adjoint. You know about that, but we write here. We write here definition. Let T belongs to V of H1 H2. Then there exists a unique operator from H2 into H1 denoted by T adjoint. Then there exists a unique operator T star, okay, from H2 into H1 such that Txy equal to x T star y for all x belongs to H1, y belongs to H2. This operator T star is called the adjoint of T. The adjoint of T. Okay. Now properties of T star. Now properties of T star or adjoint of T. Properties of adjoint of T. We write first T adjoint of adjoint equal to T. That means adjoint of adjoint T equal to T. Next, second, norm of adjoint T equal to norm of T. Third, if S belongs to B, H2, H1 or H3 right here, then is T adjoint equal to T adjoint is adjoint. Okay, now here 4, if R belongs to B, H1, H2, then R plus T adjoint equal to R adjoint of R and adjoint of T. Adjoint of R plus T equal to adjoint of R and adjoint of T. Number 5, we write here alpha T adjoint of alpha T equal to alpha conjugate adjoint of T. Okay, this one is the properties of adjoint. Now also remarkable some result with right now. Okay, some remarkable result also right now. So we write here remark. Let ST belongs to B of H1, H2 and alpha belongs to C. Then what we obtain? Then first one A equal to norm of S plus T less than equal to norm of S norm of T. And B second one norm of alpha T equal to mod of alpha norm of T. And third one is our portion. And third one will mark as 3 adjoint of T norm equal to norm T square equal to T adjoint of T norm. Now obviously another way we write norm of T. Let T belongs to BH, then norm of T equal to supremum of Txy such that mod of this such that xy belongs to this sphere. Okay, sphere of H. Next we write here let T belongs to B H1 H2, then first one NT equal to R of adjoint of T, range of adjoint of T perpendicular. Here 2 N of T adjoint equal to RT perpendicular. Number 3 RT closure equal to N of T adjoint of T perpendicular. And number 4 RT R of adjoint T closure equal to NT perpendicular. Number 5 in nullity of adjoint of TT equal to NT. And number 6 range of T adjoint of T closure equal to range T closure. Okay, so this one is some observation we also write here. Okay, if anyone interested, then she or he also check this one is right or wrong. Now we also going to some definitions of operator. Okay, that means some definition of operators. So we erase these portions and going to the definition of some operator. First we write identity operator. Identity operator. Let H be a complex Hilbert space. Let H be a complex Hilbert space. Let I be the identity operator. Let I be the identity map on H. Then norm of I equal to 1. Now we write here right shift operator. Right shift operator. Let R L2 to L2 be given by R of x1 x2 equal to 0 x1 x2 for all x1 x2 x3 belongs to L2. Then Rx norm equal to norm of x for all x belongs to L2. hence R is bounded. And norm of R equal to 1. And also adjoint of R y1 y2 y3 equal to y2 y3, this one. Then norm of R star equal to 1 for all yn belongs to L2. Okay, this one is the right shift operator. Next, we talk about an operator. Okay, next we talk about some operator which are which are matrix operator, matrix related operator. But today we stop here. Okay, today we stop here.